Welcome to the AP Calculus BC video for skill number 209. I can find limits of functions from graphs. Alright, we'll start our notes on page 209a. Suppose a function f of x is defined when x is near the number a. What that means is if we have a curve and we've got some spot which we'll call a, the function is defined. It exists really close to a, or near a. So we can write that the limit as x approaches a of f of x equals L. And that kind of means as we approach a, the limit of the function approaches this value which we'll call L. Now, we don't want to think of it quite as the same thing as the y value of the function at that point, because there's something sometimes that's a bad way to understand it. But loosely, that's sort of what's going on. Below I've got a graphical example. We've got the function f of x equals 1/2 x, and as the function approaches x at 4, the function approaches 2. So f of x approaches a value of 2 as x approaches 4. So the limit as x approaches 4 of 1/2 x is 2. And right now I know it just looks like you're looking at the y value, but shortly here you'll see why that's not always the best way to interpret what's going on for calculating limits. And sometimes that doesn't even work for us. So, the graph does not necessarily have to be defined at x equals 4, nor does f of 4 have to be 2. So you could have a function that looks like the line that we've drawn, and then at 4 there's a hole. So still, you get the same idea that we're approaching 2 as x approaches 4. And this statement would still be true, except for our function has now changed. But the idea is still the same. If you assigned a value at 4, so we had our line that was moving along, and right when it got to 4, it jumped up to some value of 7, and then dropped back down and kept going. Still, the limit as x approaches 4 would be 2. So we'll see this on the next page. Here we have 3 examples, very similar, where you've got the curve on all 3 examples, and like the last example, it was actually defined. So the limit as x approaches a of f of x is L. Even if there's a hole, and even if there's a hole with a jump to a different point, a different y value on the graph. So this statement is true for all 3 of these graphs. Where we start to run into some problem is the fact that the limit does not always exist. And I've drawn a step function below, and this is a case where the limit doesn't exist. Since the limit of f of x approaches different values at the left side and right side of 3, so we'll at 3, the function from the left side is approaching this value, which we'll call 1, 2, we'll call 0, 1, 2. And from the right side, it's approaching a different value of 3. So from the left, it approaches 2, and from the right, it approaches 3. And because they're approaching different values, the limit does not exist. So we write the limit as x approaches 3 of f of x does not exist. A second example of a limit that doesn't exist is the function sine of pi over x. And very loosely what we have is a graph which oscillates, and as we get closer and closer to the vertical axis, it gets tighter and tighter and tighter. So essentially, at the vertical axis, the graph is oscillating infinitely at that point, and so it's not possible to determine what it approaches.
Hey, Ryan.
Hey, Billy. That hurt.
All of this connects to the idea of one-sided limits. So this is apparent with a piecewise function that we have here, y equals 2x if x is less than 1, and it equals negative 3x if x is greater than 1. And I've graphed the function. And if we want to know the limit as x approaches 1 from the left side, which we notate like this, of the graph is approaching 2, so the left-hand limit is 2, but if we approach from the right side, the right-hand limit, our graph is approaching negative 3. All right, so to recap, what we have is a broken function, and this break is often a great indicator that our left-hand limit and our right-hand limit are going to be different. If we approach from the left, we approach 2. If we approach from the right, we approach negative 3. So finally, we have the last conclusion is the limit of f of x equals L. So the limit as x approaches a of the function is the value L if and only if the left-hand limit and the right-hand limit are the same. All right, this concludes video for 209. I can find limits of functions from graphs. Thanks for watching.